Well, hello scrappers, welcome back to my channel. Mike here. Now this is by popular demand, okay? This is not something I was going to film, but I'm working with the material from Mount Baker Mining and Metals, and I've been having a lot of trouble with some aspects of dealing with it. And I offered to show you guys kind of my failed experiments, my bloopers, my intermediate results, whatever, and people chimed in the comments on that last video and said, yeah, we want to see that stuff. So here you go, this is for you. I've got all the prills from my previous experiments. Most of these are from like episode 1 and between episode 1 and episode 2 of dealing with this stuff, and I've got some of my later prills here. And what I'm planning on doing, and I think I can get one more melt out of this crucible before I throw it away because I'm not going to use any harsh chemicals in here. I'm just going to melt these prills down and I'm going to corn flake them. And then once I've got them corn flaked, which will increase their surface area tremendously, we'll try some other stuff on it. And that may be in this video or that may be in a later video. I'm not sure. We'll see how this works. So I'm going to put a little borax on there to facilitate the melting of these, and then we'll get it in the furnace. We'll get these prills melted down and we'll dump them in a pan of water and see if we can corn flake them, increase their surface area, and then I might divide the corn flakes up into a couple of different batches and try a couple of different things with them, okay? So let me find my borax and I'll meet you over at the furnace. Okay, so once again, this is something I wouldn't ordinarily film. It's something I normally do in my spare time while I'm working on other projects and just trying to perfect the process, okay? Now, one thing you guys have been telling me, a lot of you have been chiming in and say, put a piece of cardboard under your crucible and it won't stick to the plinth. Obviously, a lot of you guys watch Big Stack Casting then, because he does that. But it only works if you don't have a boil over. And if you're melting metal, usually it doesn't boil over. But the chemicals I put in here a lot of times boil over. Not expected to boil over this time, so we'll give it a shot and see if it helps. Because that crucible has had multiple boilovers, and there is a lot of stuff on the outside of it. It might melt and flow down, and you know, that cardboard might not help. We'll see. Let me get this fired up. Close that down a little bit, otherwise it probably won't want to light. There we go. And once it's hot in there, I can open that up and get some more airflow in there and really hit the turbo here. There we go. Yeah. So it's going to take a while for that stuff to melt. I'll get my pot of water ready, my tongs and everything out here, so that we can corn flake this stuff. And we'll see how it goes. Alright, I think we're just about ready. And before any of you wiseacres start chiming in the comments about me ruining my wife's pot there from the kitchen, well, that's not from my wife's kitchen. You know, give me credit for a little bit of brains, or at least a bit of survival instinct. Now, I bought that at a thrift store for next to nothing, just for things like this. Alright, so let's pour this stuff. Kill the heat. Oh, that is one hot crucible. All right, let's see what we got. Oh yeah.
got us some corn flakes. And there's a couple big chunks in there too, unfortunately. Maybe I can bust that up. Yeah, that busts up easy enough. I want the surface area, you know? I'll give you a close-up look at this stuff.
Alright, so here's our corn flakes. Stuff's still hot. Probably have to bust up some of these bigger chunks with a hammer because I want more surface area to this stuff for the next few treatments I want to give it. I was afraid we'd wind up with some big chunks, but that's okay. Alright. Okay, for one experiment I want to do with this stuff, I'm going to take about 100 grams of this stuff and I'm going to boil it in muriatic acid. Now that we've got a lot more surface area to this stuff, you know, I tried boiling one of those prills in muriatic acid, and after like 3 or 4 days, I only had etched about a millimeter so deep into the metal. But we got a lot more surface area here, and I can let this go for a very long time. So I'm going to put this stuff in a beaker and I'm going to let it boil in hydrochloric acid, and we'll see what residue is left afterwards. I'm thinking it's going to be copper and precious metals, okay? Not sure this is a practical way of doing it, but it is something I want to try. It's something a lot of you people have wanted to see tried, so we're going to do that. And then the rest of this stuff over here, well, I have other plans for it. They may or may not make it into this video. We'll see. Okay, I've got our cornflake stuff in this beaker, about 100 grams of it. Going to cover it with muriatic acid. Actually, I'm going to put a fair amount in here. And as the amount goes down over time, I will top it off, because I've got plenty of muriatic acid. And already, let me zoom in, I don't know if that's showing. Already, everything's stone cold and we've still already got a reaction going on in there. So let me put some heat to it and warm this stuff up, get this party started. And I will cover it up. Kind of get the little bit of refluxing going on in there. It's turning yellow already, so yeah, something's going in solution. Probably the zinc, aluminum, whatever. So this might take days. Another reason I wasn't planning on showing this, but you guys said you wanted to see it, so here you go. So this might take days, might take a week, until all the base metal is dissolved out of there, and we're left with probably, I'm thinking, just copper and precious metals. Might be a little bit of other stuff too that the hydrochloric acid is not going to attack. We'll just let it go and we'll see what happens. Like I said, I will top it off as necessary. Yeah, this stuff's been cooking for a while, and just as I figured, it's starting to turn green. Quite the reaction though. Quite the reaction going on. And we're chewing up that metal, so that's good. See what remains in the end. Okay, it's the next morning. This stuff, I let it boil all afternoon in the acid, then let it sit and cool off overnight. So yeah, it's turned kind of a deep green color, just as I was expecting. There's still a fair amount of metal on the bottom. I think what I'm going to do is decant off this green stuff and put some fresh acid on it and put it back on the boil. Again, I'm not sure this is an economical or environmentally responsible way to try and get the stuff out of this, but on a small scale, I just want to test and see if we can get rid of the bulk of the base metals, probably leave behind the copper and the precious metals with enough acid treatments. So, and I will dump this liquid into my waste bucket where I keep a lot of iron in there, and the copper and other reactive metals in the acid should cement out on the iron, and I'm not going to dump it down the drain or anything. So don't you do that either, okay? Alright, so I'll get some fresh acid on this and get it cooking again. Okay, there we go, got some fresh acid on it. There is a lot of black particulate matter in there, and you know, that's probably what we saw before. If you go back and you look at, what was it, episode 3, I think, where I had soaked one of my prills in muriatic acid for like 3-4 days. It was covered with a black powder, and I'm pretty sure that powder was mostly copper. This is probably mostly copper too in here. But I wouldn't be surprised if there's a little bit of precious metal floating around in there, in those black powders too. But there's still a lot of base metal there, so this is probably going to have to soak for days, boil for days, to get rid of the bulk of it. My corn-flaking didn't get the stuff as small and thin as I would have liked. So I need to work on that. So this has had 2 long boils in hydrochloric acid now. Once again, it's turned nice and green. There seems to be a lot less material on the bottom though, so it is dissolving away the base metals. So I think I'm going to dump this acid off and give it at least 1 more boil. And I'll give it however many boils it takes until we're not getting any more base metals out of this, basically. Okay, this stuff has had 3 hydrochloric acid boils over a period of about 4 days. Okay, and I don't know if you can see that, but there's a layer of black stuff on the bottom, and most of the big chunks of metal that were in there seem to, you know, my big cornflake chunks, they seem to have dissolved. Okay, so here we go. We're starting hydrochloric acid boil number 4. When I poured the hydrochloric acid, it stirred up all that black stuff on the bottom, but it'll settle and clear here shortly. So I haven't talked about what I want to do with this neck. After I get as far as I think I can go with the hydrochloric acid alone, the next step is I'll rinse it really well, the black stuff that's left over, rinse it really well, and then we'll hit it with nitric acid. And we'll run some tests on what dissolves in the nitric acid. And then whatever doesn't dissolve in the nitric acid should be precious metals. So we'll see. But we got to boil this some more. So 1 more boil at least. So as for the rest of this stuff I've corn-flaked, I want to measure out some 200 gram samples. Roughly 200 grams. Ooh, that got right up to 110 quick, huh? And I will run these through my sulfur reverse smelting process and eliminate most of the base metal out of them. And even though the prills I'm going to get are still going to be heavily contaminated with base metals, they still will be almost entirely copper. So the bulk of it will be copper anyway. It's just going to be contaminated with enough base metal that it's going to be sort of a white bronzy color. So I'm thinking I should melt those prills down, or even just use them as they are. I might not have to melt them. Is that 208? 94. 98. That's too big. Just use them as they are, maybe, for anodes in my copper refining cell, because they are mostly copper. And we'll see how it works. It might be a disaster, or it might work just fine. But we won't know until we try. So here's 3 samples I can run and get 3 prills. And 3 prills will be enough for a good run in the cell, I think. So I'll have to mix up some flux. Okay, so let me mix up a little flux here. I don't want to totally burn off all the metal. I want to get rid of a good proportion of it. So I'm going to use my recipe that tends to burn off 80% of this stuff. Alright. Put in 200 grams of soda ash. Okay, 200 grams of soda ash. 50 grams of silica. Come on. I hate this scale. Need to buy a new one. Close enough. Put in 80 grams of sulfur. Okay. Come on, up to 130. There we go. Okay. And 50 grams of borax. And that should burn off about 80% of that metal in there. Leave behind a prill that is mostly copper, but with a significant amount of tin, unfortunately, still in it, and all the base metal, and all the precious metals. At least I'm hoping so. Okay, close enough. All right, good. So there's our mixture. So I'll put this in a crucible. I'm going to use one of my new crucibles because that other crucible's pretty much on its way out. We'll get this in the furnace, and then I got two more I need to mix up. Just like that, and they can go in the furnace later. I want to get 3 prills like this. Meet you at the furnace. Let's get this stuff in the furnace and get it cooking. So I got 3 of these to do. May not all get done today. But eventually, I want 3 little prills. Well, that's going to take a while to heat up. I got to get my cone mold out, tongs, other stuff, get it all ready to go. All right, let's get this stuff poured. Hot stuff coming out. Yeah, man, the radiation coming off that is murder. Okay. Let that harden up. I'll put it in front of the fan. We'll see what kind of a prill we get out of it. Oh yeah, that's cool enough. All right, let's get that out of the cone mold and see what we've got. There's our prill. Well, that came out pretty very clean. I will save this slag where I've been saving all my other slag. Let's weigh this up and see how much metal we got here. 48 grams. Alright, that's pretty good. It's a little more than I was expecting to get, but it'll work. And I don't know if that's showing up how shiny that is. I mean, I'm sure that this is mostly copper. It almost certainly has to be. But look how shiny it is. So, yeah. So there's one down. 2 more to go. So, be back when I got all 3. You've already seen the whole process. Okay, you guys said you wanted to see the bloopers. Here's a blooper for you. I took this first prill I made, and I just tapped it on the point with a hammer. I was thinking I could flatten the point a little bit. I probably should have used my grinder instead to flatten it, because my plan was to drill a hole in it and tap it so I could put a brass or copper screw in there and hang it in the electrolytic cell. I was going to make this an electrode for the electrolytic cell. I was thinking about hanging it fat side down, so I was going to drill into the top. Well, look what happened. I just tapped it with a hammer, and this thing shattered, like so. This stuff is crazy brittle. Wow, that is really brittle. Kind of shiny on the inside, but amazingly brittle. Wow. I don't know if I can drill and tap this. I think I'll have to do it the other way. Probably drill it from the bottom and hang it, you know, skinny side down. That actually might work better anyway. So, I don't know. This stuff might be too brittle to drill and tap, though. That is some amazingly brittle metal. Very weird. So, there's a blooper for you. Hope you're happy.
Well, there's number 2. Yeah, this stuff is brittle. I just knocked one corner off of it. Gotta find it. There's part of it. Yeah, this is seriously brittle metal. Change of plans. Oops! Ha! Another blooper for you. I dropped it and knocked another corner off. This is seriously brittle stuff. So, I don't know if I'm going to be able to drill and tap this. Maybe not. Alright, I got the third one in the foundry furnace, though. We'll see. I'll find these pieces. There's a piece. Can't pick it up with my gloves on, though. It's still hot. Alright, last one. Be a little more delicate with it this time, since this stuff is so brittle. Starting to wonder if it's really even metal. Pretty darn dense, but boy is it brittle. Wow. The other prills I got were not this brittle. So, but, you know what? This has been through 2 processes. This has been prilled once already with my, back in like episode 1, episode 2, I was doing with oxidizing flux. And then it's been prilled again with sulfur. So, I don't know. This metal's been through some trauma. Don't know if I'll be able to drill that or not. This is something I haven't really talked about in any of the videos, but this highly basic flux I use on these, it comes out looking like glass when it's fresh, but I'll tell you what, it's so humid here in Florida, and this stuff is very hygroscopic, and it's very, very soft and nasty. What I normally do with these prills I make is I'll boil them in water to get the flux off before I do much with them. But these I left out overnight because it was towards the end of the day yesterday when I was done with them, and yeah, the flux on them has gone all soft and gooey and nasty, and it's very caustic. So basically, after cooking that soda ash in the crucible in the kiln, it turns into lye basically, and then lye is very hygroscopic, so it pulls moisture out of the air, plus it's very caustic. So yeah, I probably need to just boil these in some water, and while I decide what to do with them, you know, I haven't decided what exactly I'm going to do with these darn things, because they aren't turning out, you know, quite as well as what I hoped to be, so I got to think about that. So it's the next day. I soaked these in water overnight, got rid of the bulk of the nasty, caustic slag that was stuck to them, so I can handle them now without getting that black, nasty, caustic goo all over me. Did a lot of thinking overnight, and some research, and you see, I've noticed a couple of things. First off, let me zoom out. Here's our experiment with some of this stuff that's been boiling in hydrochloric acid for days and days. It's on its 4th boil now. I just took it out of the fume hood to show you. There's
some black powder on the bottom. But most of the metal I put in there seems to be gone. So any beginner level chemistry textbook will tell you that hydrochloric acid won't dissolve copper. And that's only, yeah, somewhat correct. All right. If there's no oxidizing agents around, like oxygen from the air, and if there's no other nasty metallic salts in there that can attack the copper and help put it in solution, yeah, that's true. If you're just dealing with pure copper and pure hydrochloric acid, yeah. Even so, this stuff doesn't really like to dissolve copper. Now, it's green, so we probably got some copper in solution, but I don't think this has been dissolving the bulk of the copper. I think the bulk of the copper is in this black stuff down here. But there's not enough of it. There's not enough of it. Tin, on the other hand, hydrochloric acid will dissolve tin like nobody's business. So, the fact that most of the metal down here seems to have disappeared leads me to believe that there's probably a lot more tin in this stuff than I was assuming. I also did some research last night and found that bronze alloys with a large quantity of tin in them can be quite brittle. And while these are brittle, these are beyond brittle. They are incredibly brittle. So, first thing I want to do today, we're going to apply some actual science here and see if we can figure out what this stuff is. First thing I want to do today and see if this is actually metal and not just some shiny sulfide that kind of looks like metal. Because as brittle as it is, I can believe it's not really a metal. So first thing I want to do, I want to put my ohm meter on here and see what the conductivity of this stuff is. Because if it's not conductive or it's only a little conductive, then this is probably not metal. So let's get the ohm meter out. And then, after that, I want to see if I can determine what the density of this stuff is. And then from the density of these and the density of copper and tin, which is probably the major components in here, there's probably some other stuff too, but I would say mostly copper and tin. Then we can figure out whether we're closer to copper or closer to tin or somewhere in the middle. So, yeah, we're going to apply some actual science. So let me get my multimeter out, and we'll do that first. Okay, here's my meter. Let me put it on the lowest ohm setting and turn it on. Okay, so if I short the leads together, we get down to about half an ohm, roughly. Alright. Yeah. Half an ohm, roughly. Alright, so. Oops, kicked the tripod, sorry. Damn size 13s again, they're just in the way. Alright, let me do this so you can actually see the meter while I'm doing it. And put the probes on this thing. Oh yeah, that's quite conductive. Okay, that's a metal. It's a metal. Yeah, okay. Because if this was a sulfide, it would be much less conductive, or a semiconductor, or not conductive at all. But no, this is metal. So we are dealing with metal. Okay. We've applied that much science. We know we're dealing with a metal. Okay, so let's see if we can figure out the density of this metal now. And maybe that'll give us some idea of just what its composition is. Since I can't find anybody locally to do XRF on it, and you know, I could send them out to somebody, but it's going to take time, and they're going to charge me an arm and a leg. So, you know, again, in the comments, if you know somebody who will do our XRF cheap and near me, Central Florida, let me know. Okay, so let's see if we can figure out the density on this. See if we can do some science without XRF. Okay, let's try doing a little actual science here and see if we can figure something out. Let's see if we can figure out the density of these. I've been suspecting for a while they might not be dense enough to be mostly copper, but of course that's just a vague suspicion I've got. Let's see if we can figure out their actual density. Then we'll look up the density of copper and tin and see if we can figure out what they really are made of, because that's probably the two main components here. So I got my most sensitive scale out here. Let's see what all these weigh, including all these little bits I knocked off the corners. 144.92. So 144.92 grams is the mass that we have. Now let's see if we can figure out the volume on this stuff, okay? Graduated cylinder here. Let's see if I can get these in without breaking it. I actually had to grind the tips off so they would fit. Get them all in here. All these pieces. Okay. So what I'm going to do now is I'm going to fill this up to the 100 milliliter level with water. Okay? Close to 100 milliliters as I can get it. Even 100 will make the math easy. And remembering my chemistry class, I got to look for the meniscus here and get it up there to the level. That's actually a bit much. Oh, that's about perfect. That's right at 100 milliliters. Okay, so now what I'm going to do is I'm going to pour this liquid out of here without dropping all this metal into this beaker and blasting the bottom out of it. So this is not going to be 100% precise, but it's going to give us some idea, some rough idea of what the volume of this material is. So I'm going to put this water back in the beaker, or back in the graduated cylinder. And the difference between what the volume is now and 100 milliliters tells us the volume. Come on. Get those last few drops, but I don't want that piece of metal in there. Yeah, we're going to be a few drops short. So this is actually going to give us a number that's a little bit higher on density than we're actually getting. So it looks like about 82 milliliters is what we got. So the difference then is, what is that, 18 cubic centimeters? 18 cc's is what we've got for volume, and 144.92 grams is what we've got for weight. So we can do a little bit of elementary math here and figure out what our density is. Okay, let's do a little math. We know the volume and we know the weight of this stuff, so let's do a little elementary math here. I've got the calculator app open on my phone. I hope you can see that. Oh, I better take it out of hexadecimal mode. I was working on a project for the second channel where I do retro computing stuff. So, hey, check out the second channel when you get a chance, if you're at all into retro computing or electronics. Alright, so we're in decimal mode now. So we had 144.92 grams was our mass. And then our volume was, what, 18 grams, right? Yeah, 18 grams. Divided by 18 equals 805 for the density. 805 grams per cubic centimeter. Let me write that down before I forget it. Okay. Now let's see what the density of the metals we're working with is here. Or at least the metals we assume we have in here. Alright. Okay, so according to Mr. Google, and again I hope that's showing up, the density of copper is 8.96 grams per cubic centimeter. So almost 9 grams per cubic centimeter. Well, we're down to about 8. So, okay, so yeah, we got a lot of pollution with a much less dense metal than copper here. So what does Mr. Google say the density of tin is? Mr. Google says the density of tin is 7.6 grams per cubic centimeter. So, yeah. Take a little more math to figure out what the ratio of the two is, but we've definitely got, I would say, a lot of tin here. A lot of tin. There's definitely some copper in there. Definitely some copper. but there's a lot of tin here. There might be some other metals in there too, some other lighter metals. Let's see, there was a little bit of titanium in the assay report, so I don't know if the titanium is getting burned away with the sulfur. It could be winding up in here. There's some other stuff in there that might not be getting burned away that's lighter than copper. I suspect we've got a whole lot of tin in here. Probably close to half tin, I would guess, just looking at these numbers off the top of my head. Okay, I did a little number crunching, and given the density of this material, the best fit, assuming that they are made just primarily of tin and copper, which I know is a dangerous assumption, but assuming that, then the best fit for the density we have here is about roughly 55% tin, 45% copper. So yeah, there is a whole lot of tin in these things. And you know, even if there's other metals present, you know, they're going to be present in fairly small amounts. We've gotten rid of a lot of the other stuff. We've gotten rid of the iron. I'm sure we've gotten rid of aluminum, magnesium, zinc, you know, all the stuff above iron. I mean, there might be some other light metals in here. This is everything under the sun's in the assay report. So there could be some other light metals in here. The percentage of copper might even be lower. Or there could be some heavier metals in here. There could be some lead in here. That would make these, bring the density up. Of course, that would again would make the percentage of copper lower. There's probably also, you know, I'm assuming the precious metals are in here somewhere. The gold, the silver, the platinum group metals that were present in the material should be in here somewhere. But again, they're going to be in small quantities. I think we can probably ignore them and just assume that this stuff is mostly tin and copper, and actually mostly tin, okay? So something's not right here. In spite of what the reactivity series of metals tells us here, we are not getting rid of the tin. The tin is either staying behind, or we are getting rid of copper instead of the tin. I don't know. But for some reason, copper is the most abundant element in this stuff. But by the time we've been through my treatments here, it's less abundant than tin. So I don't quite understand that. I don't quite understand why the pyrometallurgy isn't working out the way I expect, either with the oxidizers, sodium nitrate, potassium nitrate that I've used. I've also used manganese dioxide. I tried a lot of different oxidizers, and it wasn't oxidizing away the metal the way I expected. Then I switched to sulfur, which did a much better job of oxidizing away the metal. Yes, sulfur is actually an oxidizer. It's actually immediately below oxygen on the periodic table of elements in the same column. So sulfur works a lot better. I can actually oxidize away all the metals if I want and wind up with nothing left in the slag. But you know, it's not taking the stuff out preferentially higher up on the list for some reason. I don't quite get it. But I'm new to pyrometallurgy. I may be missing something. Okay, anybody out there has any thoughts on this, leave me a comment, suggestion, idea, whatever. I'd appreciate it. So I'm not sure where to go with these. You know, if these are actually 55% tin and at the most 45% copper, I don't know that they're going to work as anodes in an electrolytic cell. I think all that tin is going to cause us problems. Man, I hate tin. It is just always in the way of getting gold, one way or another. So I need to think about where to go with these. And oh, they're tarnishing after their water bath. They were nice and shiny before that, but at least I got rid of all that black caustic slag off of them. I need to think about where to go with these from here. I think my original idea is kind of out the window. So, hey, you guys wanted to see the failed experiments. Well, here you go. I think this is pretty much a failure. Need to wait and see what's left in the bottom of that beaker after the acid is done chewing through the metal in there. Then maybe I'll have some kind of idea of how to proceed. So here's something curious. This stuff has gone black. It was just light green before, quite translucent or transparent, light green. Overnight it's gone black. Very, very odd. Very, very odd. Okay. I don't know. It got kind of chilly last night. Maybe something came out of solution, precipitated out of solution with the cooler weather. I put another splash of hydrochloric acid on it and put it on the heat, and thinking that the stuff might go back into solution, but nothing happened, so it's still quite warm. Very curious. So I guess I'm going to have to decant off the liquid to see what's going on the bottom of the beaker, because it has gone quite opaque. We'll see if basically we're done dissolving metal out of this or not. Well, I do still see the occasional bubble rise, which tells me there's probably still some kind of activity going on in there. Maybe I'll leave it for a little while longer. I am working on some other stuff, so maybe I'll just leave it for a bit longer, then decant it off and see what's in there. Okay, so let's have a look and see what's under this really dark green liquid here. See what's left. I left this sit overnight again because there was still some bubbling, but that seems to have subsided. It's a pretty dark green-brown liquid. See how much metal is left in the bottom of this thing. It looks like it's mostly just powder. Yeah. Looks like we just got some black powder down in here. There are a few chunks. But it's mostly black powder. Not very much. I would say probably, in spite of what the chemistry textbooks tell you, I think we've dissolved away most of the copper too. Because I'm pretty certain I've determined this stuff's about 45% copper. So let me give this a couple of rinses with some distilled water. And then I think what I'm going to do is I'm going to hit what's left in here with some nitric acid and see if we can dissolve away anything else. And then whatever remains from the nitric acid treatments, I'm going to dissolve in aqua regia and see if we get any trace of precious metals out of it. Yeah, let me wash the chloride out of it before I put the nitric acid on it. So I don't want to make aqua regia prematurely, you know. Some of that fine black powder's coming over, which I'm not really happy about. But okay, I'm going to give this a couple more rinses, and then we'll hit it with some nitric acid. Alrighty, I've got the beaker with our black residue in it, in the fume hood. I'm going to put a little bit of distilled water on it. Just a little bit here. About 40-50 milliliters maybe. Then I'm going to put some nitric acid on it. And we will see what we will see. Yeah, unfortunately, it looks like we've dissolved away the bulk of the copper. So I was hoping I could get a weight on the copper in there and see if it kind of confirms or refutes my theory about what the percentage of material in this stuff is. But it doesn't look like I'm going to be able to do that, because I'm pretty sure that dark green liquid I decanted off contains a lot of copper. So I'm going to let this warm up and see what kind of reaction we get. Give it a few minutes and see. Whatever that black stuff in there, I'm sure it's going to start going into solution pretty quick. And anything that's left behind by this treatment should be precious metals. And what goes into solution, if there's any copper left, it should be copper. If there's any silver in there, the silver should go into solution. So we'll see what we get. I can test for silver, and later I can test for precious metals. So we'll see what we get. Well, not a lot of activity, which I'm surprised about. This has come up to temperature. I actually put a little extra nitric acid on it, and really there is not a whole lot going on in that beaker. The liquid has turned greenish, so there must have been a little bit of copper left in there. But really, most of that black stuff is not dissolving. So I'm thinking that that black stuff is either, might be a little optimistic to think it's precious metals, but it's certainly not base metal. So I don't know what's going on. I'm going to let it cook a little while longer, and then I'll decant the liquid off and test it for silver, because any silver that's in there should be dissolving in it. And then I'll put some aqua regia on it and see what happens. See if that black stuff dissolves in it. So, but I'm just going to let it cook for a while. No rush. I want to get any kind of usable result here. Well, this has been on here for quite a while. I'm not really seeing any further reaction in there, so I guess whatever the nitric acid could dissolve, it has dissolved. So I'm going to take this off the heat. Let it cool down a little bit, decant off this greenish liquid, and then we'll put some aqua regia to it and see what that does. Okay, I'm going to decant off this blue-green liquid here, and we'll see what's left behind in the bottom of the beaker. It's like some very fine black particulates left behind in there. Well, now I've got them all stirred up, so I will let them settle and then decant it off. Let them settle towards the spout end of the beaker. Then I'll decant the liquid off. I don't want to take that black powder because that may be precious metals. Don't know for sure, but it might be. So I gotta let that settle again. It gets stirred up easy. Okay, I have decanted off this blue-green fluid from this really fine black particulate in here. So I'm going to let that settle. It's kind of turbid, so I'll let that settle before I test it for silver, so I can get a sample of nice clear liquid. We'll put this back in the fume hood. I'm going to put some aqua regia on it and see what happens. See if this stuff goes into solution with aqua regia. It didn't go into solution with hot dilute nitric acid, but we'll see what happens with aqua regia. Okay, let's hit this stuff with a little bit of aqua regia. First, we're going to put some muriatic acid on it. 100 milliliters or so, that ought to be enough. Lid it up. We turn the heat on, just sort of medium heat, not too much heat. And now nitric acid. So we've tried hydrochloric or muriatic acid by itself. We've tried nitric acid by itself. Put the two of them together makes something special called aqua regia, which is a much more powerful acid that can dissolve even precious and noble metals. So we'll see what happens with that as it warms up. Well, we've got some bubbling going on, so I would say some kind of reaction is happening. That's good. I was starting to wonder if that black stuff was inert, but it's not inert to aqua regia, so it seems to be going into solution. Good. Excellent. This is a really good sign. First off, I've turned the heat way down, so that's not boiling. That is a reaction going on in there. The orange fumes that we've got going on in there, that means metal is going into solution. That's the only time you get those orange fumes is when there's metal going into solution. So some kind of metal is dissolving in that aqua regia. Metal that wouldn't dissolve in hydrochloric acid and metal that wouldn't dissolve in nitric acid alone. So, not going to get my hopes up too high. We might be getting some precious metals in solution. We will see. We'll let this reaction go to its conclusion, and then let this cool down and we'll test it. Alrighty, so the reaction here seems to be done. So that's the aqua regia that we've dissolved the residue in. Now this stuff over here has had a chance to sit. This is what we dissolved in nitric acid alone. So as you remember, we had 100 grams of material, dissolved away most of it just in hydrochloric acid boils. What didn't dissolve away in them, we put in nitric acid and cooked in nitric acid for quite a while. And then what didn't dissolve in nitric acid, we put in aqua regia. And there's still a little bit of residue in there. I'm thinking that's probably borax from when I corn-flaked this stuff. Okay, so don't have XRF, but you know, chemists were able to figure out stuff long before there was XRF. So I think I've already figured out that material I processed after corn flaking with my reverse smelting, I think I figured out that it was about 55% tin and at most 45% copper. Okay, using some good old chemistry, common sense. So let's see what we've got in this stuff here after dissolving it all away in various acids. First we'll do this blue-green fluid here. So this is the stuff that we dissolved in nitric acid. It's had a chance to settle, so it's nice and clear. It's got some stuff floating on the top, so I'll insert the pipette below the floaty stuff and above the stuff on the bottom, and get a couple of pipettes of this stuff and put it in this beaker over here. Now this other beaker over here contains some tap water that I've added a little supplemental hydrochloric acid to. So if there's silver dissolved in this stuff here, we should see the stuff in this beaker go cloudy. So the nitric acid should have dissolved any silver in there. Very slightly cloudy. Yeah. So, okay, so we've got some silver dissolved in here that came out of that stuff. Put a little more in, see if we can make it a little cloudier. Oh yeah, it's clouding up nice. Yeah, we definitely, let me zoom in on that for you a little bit. See how cloudy that is? See that? So we've definitely got some silver dissolved in here that we got from that corn-flaked material. Okay, so we've isolated some of the silver. Probably about all the silver, I would imagine. Now as for this stuff over here, let me put the lid back on this. Keep it clean. Oh yeah. The longer this sits, the cloudier it gets. So there's some silver there. Okay. So we figured out that one of the minor constituents of those cornflakes is silver. So now over here, this stuff, let me put that down in there. Aqua regia is nasty stuff, so don't want to spread it around. I'm going to get a little bit of this in a pipette. Well, that's way more than we need. Put it down here. And here I have some stannous chloride solution. Let me zoom in on the spoon, so hopefully you can see what's about to happen. See the color change. So, a little bit of stannous chloride solution on this. See that purple color? I mean, it's mostly orange and brown, but there is some purple there. Or violet, whatever you want to call it. There's some purple there. Purple is the color of gold in solution. Not a lot. I would say just a trace. But yeah, we got some gold in solution there. Okay. So we found some gold. And now this overall orangey color, this could be platinum group metals too. But there was definitely some purple of gold in there before it kind of went orangey brown on us. So, alright. So I guess we figured out a few things in this video, even though it was frustrating and had a few bloopers in it. We figured out that, well, there's silver in those cornflakes I made. We figured out that there's some gold in those cornflakes we made, maybe some platinum group metals. We've also figured out that the prills I made by reverse smelting the cornflakes are most likely about 55% tin and 45% at the most copper. So, okay. Even without XRF, I think we're figuring some stuff out here. So that's good. So another thing we proved was what a lot of you suggested, and what I knew was possible from the beginning. If you just dissolve away everything in acid, yeah, you'll be able to get the silver, you'll be able to get the gold, you'll be able to get the platinum group metals. Yeah, that'll work. Problem is, you know, I used about 4 liters of acid to dissolve 100 grams of metal, and created about 4 liters of waste that now has to be processed. So it's really not an economical or environmentally responsible or sustainable method of doing it. Yes, it'll work, but it's really not the best way. The tin definitely isn't behaving the way I would expect it to. So let me get my reactivity series of metal sheet out again, and let's take another quick look at it. Okay, let me zoom in a bit. All right. So the main bugaboo here, the main problem is the tin. I am not getting rid of the tin. Nothing I am doing is getting rid of the tin, which I don't quite understand, because I can get rid of the copper easy enough, but the copper should be less reactive than the tin. The tin should go first, but it's not working out that way. So I've been watching the videos by Jason over at MBMM where this stuff came from, and Jason's having a lot of the same issues with the tin. He can't seem to reduce the tin beyond about 50% of what he started with, and to do that he had to dilute it with a lot of extra copper. So I mean, that's a possibility. I have copper I can dilute this stuff with and make the tin a minor component again and wind up with something that, you know, might work in an electrolytic cell. It just seems like cheating to me. I wish there was a way to just get rid of the tin, and there probably is. I'm just not seeing it. If anybody out there has a lot of experience with pyrometallurgy and knows what I'm doing wrong, or has this good suggestion or good idea, anybody has any good ideas or suggestions, leave me a comment. Let me know what you think. You know, because I would really like to just be able to get rid of the tin and everything above the tin and leave all this other stuff below the tin in the prills. And that would be very, very helpful. But so far it's not working. But yeah, this works. This works, and a lot of you suggested it. Just digest everything in acid, and in the remaining sludge you'll get your silver, you'll get your gold. Yes, it works. I knew it would work. It's just not practical. So, still looking for a pyrometallurgical way to do this, and I'm going to give it some thought and do some more research, and we'll see what I come up with by the time the next video comes out. So thanks for watching this one. Subscribe to see those future videos when they come out. Check out my second channel, ElectroGeek64. Good stuff going on over there, lots of new content. Lots of electronics and retro computing stuff over there. But once again, thanks for watching this video, and I'll see you in the next one. Bye.